This demonstration that I'm going to illustrate a relationship of what happens when you add one volume of a substance to another. It's entitled Vanishing Volumes. You know, many concepts in chemistry are difficult for students, be it first year or beyond, because what we have to do is we have to make mental images of the concepts that we're talking about, because not everything that we're talking about is visible to us. One of those concepts deals with intermolecular attractive forces. As well, we also have intramolecular attractive forces, intermolecular forces between distinct particles, separate molecules, whereas intramolecular attractive forces are forces within a single molecule or particle. Okay. The other difficulty that we find students encounter is their preconceived notions of things, ideas that they come into play when we're talking about a particular concept. For example, at a very early age, it may be as early as 2 years of age or so, we find that if we were to pour a volume of a liquid from one container into a container, say, of a different shape or of the same shape, and this is just water now, that volume is conserved. I haven't lost any. If I did that with a different shape container, earlier than a couple of years of age, a child might think that the quantity of the liquid has changed. But after a certain point, suddenly they realize that the volume hasn't changed, it's just the shape of the container. What happens, though, when we use two different types of liquids and we add one to the other? Okay. Are those volumes conserved or not? Well, we're going to take a look at that. But the problem that we encounter as well is that up until the point at which we discuss forces of attraction, we've discussed stoichiometry. And what's conserved in stoichiometry? Well, mass is conserved. Why is mass conserved? Because atoms are conserved. So that can cause some difficulties with students. If atoms are conserved and mass is conserved, why too isn't volume conserved? Well, it turns out for certain reactions, volumes might be conserved, but they don't have to be. Okay? We're going to take a look at a couple of different demonstrations dealing with additions of volumes and see that, in fact, volume is not necessarily conserved. The first demonstration that I'm going to do is one involving two different liquids, one of which is water, and the other is ethanol, an alcohol, ethyl alcohol. Students, by the time they reach chemistry, have probably heard about ethyl alcohol, but they probably haven't seen it, and I'm certain they haven't come in contact with it. There's a bridge that I almost bought way back when I lived in Brooklyn growing up, but anyway. Okay, so I'm going to add some water to this tube that I have, this glass tube, and in order to see the water more easily, I've put some blue food coloring into the water. I'm also going to use some ethyl alcohol, and to do that, I want to put on some gloves. Whenever you're handling chemicals that could adversely affect you, you want to take precautions. I'm going to move in front of the lab table, and I usually do that when I'm doing this demonstration so that students can more easily see what I'm doing. So I'm going to take my tube, come around to the front, and I'm going to add the liquids to them one at a time. Now I've already found stoppers that fit this tube, and one end of the stopper I've already put some parafilm onto that stopper to help to keep it sealed. Now there's a reason that I'm going to add the blue food colored water first, and that is the water is more dense than is the alcohol. And so when I add the water first, that's obviously going to go to the bottom, but then when I add the alcohol being less dense will tend to remain above the water. It'll probably mix a little bit, but for the most part, will stay on the top. Now, to prevent spilling onto the floor, I'm going to take this bucket, and if something happens to spill, at least I'll keep that inside the bucket. I'm going to fill the tube about halfway with the water. If you're short on the alcohol, you might want to add a bit more than halfway with the water. Next comes the alcohol. And this is absolute alcohol or anhydrous alcohol. It is denatured. I'm going to add this slowly at first because I want to reduce the amount of mixing of the two. I don't know if the camera caught it, but I certainly did. And that is, they denature the alcohol, and I can see the other liquid that was added to the denatured alcohol, and actually I could see some of those bubbles of the liquid going down into the water. They're being more dense than the water. Now this next step of putting the stopper on, if you push too hard, you're going to create a pressure down below that's enough that might send that stopper off. So this is a rather crucial step here in ensuring that you don't have to start over and B, empty the bucket later on. All right, I'm going to seal this as best I can with another piece of parafilm, just a wax type paper. Now, I'm going to hold finger on that stopper. I'm going to reach down and grab the other stopper, holding that in place. And now I'm going to proceed to invert this, and you can see there's an interface between the two. Remember, I filled this up virtually to the top. And I'll ask the students, do you see that bubble there? What do you think's in there? First response, an air bubble. Okay, fine. So the ends are no longer sealed and liquid's pouring out, because if air can get in, the liquid should be able to get out. Well, wait, those ends are still sealed. So air didn't get in there, did it? In fact, the bubble's getting larger as I continue to do this. So what could be in there? Well, what did I put in there? Water and alcohol. But I didn't put in any gaseous water or gaseous alcohol. So what could be in there? Well, the question then is one of seeing if they can figure out, well, what can happen to a liquid? Well, could freeze. The temperature hasn't gone down. It could boil. Well, the temperature hasn't gone up. Liquids can evaporate as well. And so eventually we get around to the idea that inside that bubble, it's not a vacuum, but it's vapor, gaseous water, and gaseous ethanol. And yeah, definitely on the level with that. Now, with an AP class, you can take this one step further. You can ask them to calculate the pressure of the water, gaseous water, and the pressure of the gaseous ethanol in that bubble using, if you know the total volume, and you know the amount of water that was added and the amount of ethanol, and you know the densities of the two, you can figure out the mass of each. You can then get the moles of each. You can get the mole fraction of each. From that, you can use Raoult's law to get the partial pressures of each of the gases. If you know the you need to know the temperature as well. So you can do a whole host of things with this. Okay. Now the question becomes not only what to do with this, now that we have it, but also to explain some of the chemistry. Before I do that, I'm going to take the stopper out, and if you get the students to be real quiet, which isn't always that easy, you remove the stopper. I'm going to put this close to my microphone, and perhaps we'll be able to pick up the sound. There was a little sound there. The sound was air rushing in to the partial vacuum that was created when those two liquids formed not a vacuum, but a pressure that was somewhat below that of room pressure. All right, I'm going to put this aside now, and we're going to take a look at an explanation as to what happened. To do that, I have a chart that I'm going to take a look at, and that's on the easel. So we'll go to that chart. By now, students know the formula of water, I would hope, and perhaps the structure of water, but maybe not. We can talk a little bit about that. Water is H2O. It does have hydrogens bonded at a certain angle and a couple of non-bonding pairs of electrons. So we can focus on one of the water molecules right here. Ethanol, or ethyl alcohol as it's known, C2H5OH, has an oxygen with two different non-bonding pairs of electrons. bonded to the ethyl group, the C2H5 group, and then as well a hydrogen. Based on the differences in electronegativities of the atoms here, the water is a polar molecule. And the negative end of that polar molecule, negative end of the dipole, are the non-bonding pairs of electrons on the oxygen. In the ethanol molecule, the hydrogen bound to the oxygen is not sharing the pair of electrons with the oxygen evenly. And so the hydrogen appears as if it is a partial positive charge, the hydrogen that's bound to the ethanol. And that partial positive charge can interact with the non-bonding pairs of electrons, one of the non-bonding pairs of electrons on the water molecule, creating what is known as a hydrogen bond. Likewise, water can hydrogen bond with itself. Ethanol can hydrogen bond with itself. But with all of what's going on, and knowing that the water molecule's structure in the liquid state is relatively open, meaning a lot of space there that's not occupied by anything, the interactions, the additional interactions, cause those molecules to get closer to one another, thereby reducing their total volume. And what we observed is just that the total volume of those two liquids is less than the sum of the individual liquids. And that's our vanishing volume when we look at two different liquids. Now that's difficult to see for students. It's difficult for me to envision that. So I have another demonstration illustrating how we can show that volumes are not necessarily additive. And this is one that we can see. So we're going to go back to the table. For this, we don't need the gloves, so I'll put those aside. We're going to take a look at solid state. I have here a container in which I've put 1-inch styrofoam spheres, and I've put them in randomly. We can get a close-up of this and see just how spheres can pack. Sometimes they pack inefficiently, and sometimes they pack efficiently. Efficient packing is what's called close-packed structures. So I'm going to take a look at a visual of this at the easel. So let me remove that of liquid state and take a look at that of a solid. Okay. Now this represents what we're seeing in that particular container. And I've taken the liberty of outlining a couple of different types of packing. One of which is simple cubic. And that's illustrated right here with the blue outline. Okay? And that's just one face of the cube. It's not a real efficient way of packing of spheres. There are other much more efficient ways of packing. For example, we have, outlined in black right here, something known as hexagonal close packing. Hexagonal close packing involves one sphere surrounded by 6 other spheres in the same layer. Much more efficient way of packing. And then we have another way, and that's what's called face-centered cube. And what we have then is a cube, 4 spheres, with a sphere in the center of each of the faces. And that is a rather efficient way of packing. There's also something called body-centered cube, but that's not easily seen on this, so I didn't outline it. Body-centered is where you have a sphere in the center of a cube. That's known as body-centered cube. With this close packing results in a couple of different arrangements, a couple of different types of what are called holes in between layers. There are 2 different types of holes. There's something called an octahedral hole and something called a tetrahedral hole. Now, an octahedral hole is one in which we have on consecutive layers 3 spheres on one layer and 3 spheres sitting on the next layer, rotated slightly. And we could actually fit, in the space between those 2 layers, we can fit a smaller sphere. And that type of packing, known as octahedral, or a type of hole known as an octahedral hole, is a result of the sphere in that hole seeing above it 3 spheres and below it 3 spheres. And the term octahedral doesn't mean that there are 6. The term octahedral comes from the idea that if you were to construct a 3-dimensional object, it would have 8 sides to it. But it's a result of 6 spheres surrounding a central sphere sitting in that hole. Octahedral holes are relatively large compared to the other type of hole, which is known as a tetrahedral hole. Tetrahedral hole is where on one layer you have 3 spheres, and sitting in the layer above it, right in the hole created by those 3 spheres, is another sphere. So if you fit a smaller sphere inside it, in that hole, the tetrahedral hole, that sphere would see around it in its environment 4 spheres. Octahedral holes are much larger than tetrahedral holes. As well, if you were to count all the spheres in there, you'd have, in theory, you would have as many octahedral holes as you have close-packed spheres. For tetrahedral holes, you'd have twice as many tetrahedral holes as you have close-packed spheres. But now let's take a look at a visual, and that is actually seeing what happens when I take 2 different solids, spheres of different sizes, and add them. So we're going to go back to the table. I'm going to take the top off and see these are styrofoam spheres of 1 inch. And the total volume is whatever the volume of the container is. I have here some BBs. These are orange. They're a lot easier to see. And I'm going to pour some of these into this container. Now, it's obvious to students at this point in their career that these large spheres occupy a certain volume. The small spheres occupy a certain volume. Let's see if volumes are additive. I haven't exceeded the volume of the container, and if I shake this up a little bit, those small spheres can actually distribute themselves throughout the structure. And some of them are actually fitting inside those tetrahedral holes. The octahedral holes are pretty large compared to these spheres, and so they're probably not going to stay in the octahedral holes. And actually these spheres some of them are these small spheres are so small compared to some of the holes that they just go right to the bottom. But one can, perhaps, in rotating this just right, there's actually a sphere right there sitting inside the hole created by a tetrahedral hole. And to create the actual tetrahedral hole, one would put another sphere right on top. But if you put a sphere right on top, you wouldn't see that sphere in the tetrahedral hole. So we wouldn't do that. There's another one here that's sitting in the hole created by one of the layers of an octahedral hole. So you could point that out to your students if you got lucky the way I did and actually had them sitting in there. Either that, or you can physically place them in there and show them that. So this is another way of showing that volumes are not necessarily additive. And as a result, another way of demonstrating that in processes, volumes are not necessarily conserved. And we now have an idea as to why volumes are not necessarily conserved.